All right. I always forget to record. Okay, so now what we'll be interested in is yeah, so hey guys, I tend to forget to hit the record button. So if I'm not recording, let me know. Okay. All right. Now, once you have established a steady state current, okay, what we're going to do is what you learn later in the chapter. What you're doing is you're storing energy in the inductor, and the energy being stored, energy is stored in the form of magnetic fields. The energy stored in the magnetic field that's created within the inductor. Okay, and now when you eliminate the battery, flip the switch from there to there. Okay, actually let's go. Okay, so here we go. So this is the circuit. So here's the EMF. The switch has been closed, and what you have done is you've established a steady state current. And whenever there's a current flowing in an inductor, there's a magnetic field inside the solenoid or the inductor, and there's energy stored in the magnetic field. Okay, so now what we're going to do is when we flip the switch from here to there, what you're doing is you're eliminating the battery, you're removing the battery, and you see there's still a current flowing in the circuit. You remove the battery and there's still a current flowing in the circuit. So how is this current flowing is a question. And that's what I was saying there. Okay, so you had stored energy in magnetic fields there, and that was driving the current. Okay, so the energy stored in the inductor was driving the current, and it drives the current for a small time, and then the current goes to zero. Now, if this inductor wasn't present, and you switch the flip the switch to here, the current would have gone to zero instantly. But because of the presence of this inductor, you are able to get a non-zero current for a while. And that's what we're interested. So now we want to find this expression. This I is a function of time, okay? And that's what this slide is about. Okay, so when you flip the switch over here, okay, so let me switch back to the iPad. All right. Oh, wow. Okay, so okay, so what we are interested in is now we so okay, so here was the switch. So initially you have this current flowing, and then what we're going to do is, we're going to swing the switch from so this was the steady state current, and we're going to remove the battery, and this is going to drive the current. Again, we want to find what is IT. Okay, the current is flowing in this direction, so what we'll do is the way this equation is set up in in the slides are like this. So we're going to start here and go this way. So that's plus ITR, you're going up the current. You're going against the current, so you're going from lower to higher voltage. And then here, you're coming here. Now this current is decreasing. This current is decreasing. So this inductor will set up a voltage which will oppose that. So this will be positive and this will be negative. So when you go from here to here, the voltage decreases, but we'll write it. So it'll be DI by dt, and you'll come back to your starting point. See, the thing is, di by dt is negative, so L is positive, so this will be a negative voltage. You're going from higher to lower voltage. Okay, anyway, so the behavior of this current is governed by this differential equation. Okay, IR plus L di by dt equal to 0. Okay, and that's what the slide shows you. Okay, so IR plus L di by dt equal to 0. Okay, and again, you can solve this equation. Okay, and so the current decreases exponentially. Okay, tau being the time constant, and tau is L over R. Okay, so there we go. We have the behavior of that circuit with an inductor present. Okay, so now we have learned how the current builds up in this circuit with an inductor present. And when you remove the battery, the energy stored in the inductor drives the current for a little while. Okay. All right. So what I'm going to do is I'm going to pause and let you guys ask questions.